Hi, it's Coding Jerk. Look at the following code. It's a simplified version of what I often see in wild codebases. There is a problem with it though. In case of minor network issues, service unavailability, or temporary overloads, it will just fail right away. But in the real world, where the network is not reliable, it's a good idea to reduce the probability and impact of such issues. The simplest way to ensure we will overcome them is to retry. So let's keep our fetch sessions unchanged from now and create a wrapper, try fetch sessions around it, which will handle errors, and let's focus only on it. A naive approach to retrying would be just calling fetch sessions in a loop until it succeeds. The main problem with this approach, as you can see in the signature, is the possibility of entering an infinite loop instead of returning none at some point. For example, if URL is straight wrong or there is a permanent network issue, we will run the same request again and again. An intuitive approach is to limit the number of retries. Now we will not run fetch sessions indefinitely. Notice that the signature now contains none as a possible return value. So retrying does not guarantee success, only reduce the probability of failure. Anyway, this function limits number of retries, but it doesn't have any limits or guarantees on how long it can run. So with this approach, the runtime of try fetch sessions is unpredictable. That's why in practice, most of the time we will use timeouts. An easy way to implement it is to save the start time and then check if the current time exceeded by the timeout. It's a wrong approach though, because we can easily exceed the timeout by indefinitely long amount of time. For example, after a couple of iterations, we could end up with current time being 1 second less than our start time plus timeout. In this case, nothing stops our request to run for something longer than this spare second we have. So after it finishes, we could exceed our timeout by a mile. To fix this, it's either our underlying function should support timeouts natively, or we will have to write our own implementation on top of it with some sort of cancellation, for example, using threads. Let's assume our fetch sessions supports timeouts by any means. So in our retrying function inside the loop, we now need to calculate the spare time we have to pass it further. This implementation is correct, but can be improved. But let's do a little side quest before we continue with important stuff. Did you notice that this start time plus timeout doesn't change between loop iterations? So we can calculate it once and call it deadline. Another thing is that in loop condition, we can move that start time term, so it's actually also our deadline. And now it replaces start time completely. Similar to how we can calculate the deadline from the timeout, we can also calculate the timeout from the deadline. Knowing this, we can either have a request function which supports deadlines or create our own version on top of it. And with it, we can simplify our retrying function by passing our deadline instead of calculating spare time. And one simplification further, just get the deadline instead of timeout as an argument. This version has exactly the same behavior as the timeout version, except it's way shorter and cleaner. There are two downsides. First, if we want to pass a timeout, it will require us to calculate the deadline first. And another downside is that it's harder to have a default value for the deadline since it's a runtime dependent value. At least that's true in Python, my most used language. But anyway, I prefer deadlines to timeouts in my code everywhere. They're almost always easier and cleaner. And to finish with deadlines, one more example why I prefer them over timeouts. Imagine you have multiple operations to do sequentially in a given time frame. With timeouts, we have to calculate the spare time we have left every time for each operation. In case of deadlines, it's much cleaner if underlying operation supports deadlines natively. And even cleaner if we accept deadline in the top-level function. Okay, let's get back to our retry code. So in practice, in addition to limiting the running time, we could also want to limit the amount of attempts. It's not a good idea to run the same request 1 million times in 10 seconds, right? Even if we can run it that many times in that time frame, it's a waste of resources and we don't want that. So we could take our max tries argument from the beginning and use it together with deadline. This way we avoid exhausting resources, but this creates another issue. Given a timeout of 10 seconds, if our first 5 attempts fail in 1 second each, we will return despite the 5 seconds we left to retry. So it would be better to change our approach a bit. Instead of limiting number of tries, let's add a delay between attempts with a simple sleep. Since with any big enough delay, it's impossible to do too many requests in a given time frame. So now we do a try, then sleep, do another try, sleep again, etc. until they either succeed or reach the deadline. So our effective use time will be closer to the given timeout. Actually, we will need to be careful since the current implementation we will sleep one more time after the last attempt. Simple check will fix that. So we will drop that user's last sleep and stop before exceeding the deadline. Okay, but how do we choose the good delay value? If it's too big, in case where the server recovers quickly, there will be unnecessary wait time. And if it's too small, in case of late recovery, we will waste more resources in failing attempts. So we need to find the balance here. Somewhat universal approach is to use the exponential backoff strategy. To demonstrate, let's switch to a 60-second timeout example. When we fail first time, it's reasonable to try again quickly, since it could be just a transient issue. Or we may end up connecting to a healthy replica if the service is behind a load balancer. So first retry could be after a short delay, for example 1 second. If it fails again, it's less likely that the issue is transient. But it's still possible, so we can wait a bit longer, for example 2 seconds. From now on, with every failed attempt, it's less likely that the issue will resolve quickly, so we can increase the delay more and more each time. And this approach, where a delay increased by a certain factor each attempt, is called exponential backoff. Since we can calculate the exact delay for nth attempt as this way. In case of persistent issues, we reduce the load on the system, and in case of transient issues, we can recover faster. It's a good as default choice, but there are also other valid strategies. Fixed backoff is that we implemented first. It's simple, it creates predictable retries, and it's actually good choice for UI. The user is waiting for the result. There is also Fibonacci backoff, where delay increase following Fibonacci sequence. It's a bit less aggressive than exponential backoff, but very similar in practice. There are many other strategies, like polynomial, linear, but let's focus on the exponential since it's the most useful one. So let's back to our function and implement it in code. First, let's replace our constant delay with an initial delay and a backoff factor. Then, inside the loop, let's keep track of the current delay. This approach is pretty good for most systems and almost production ready. But you guessed right, there is a problem. Imagine they have multiple services using single API with this retry logic. They are making requests normally without any pattern. But then something happens to our API and it holds all the requests. Maybe it's a database lock or CPU spike, doesn't matter. So our clients all start waiting for the response. And at some point, database restarts due to watchdog and all our clients get error at the same time. Our clients use the backoff strategy to calculate the delay, then they sleep and boom, they all try again at the same time, creating another load spike. Then they all fail again, calculate next delay, and send all requests at the same time, and again, probably creating a load spike even worse than one that led to the failure in the first place. This cascading effect is known in distributed systems and called retry storm, or more generally, the thundering heart problem. The usual and good enough way to fix it is to make our delays less predictable by adding some randomness. A naive approach would be to keep our calculated delay, but add some random value to it, for example between -10 and +10% of the delay. Even worse would be adding a random value between some constants, like from -100 to +100 milliseconds. It would help just a bit, but not enough in case of big delays. First good approach is called full jitter, and you just have to take a random value between 0 and the calculated delay. It gives too much randomness, and in practice you may want to at least cap the minimum delay. And maximum too, since waiting for 30 seconds between retries is most likely overkill. Let's move the capping logic to its own function. Now, a good approach which balances between predictability and randomness is called equal jitter. Idea is to split value in two halves and randomize only second half. Or, in other words, to select the value between half of delay and full delay, which is the same thing. And final algorithm is called decorrelated jitter. You remember that exponential backoff can be written as a relation on the previous delay? And in the correlated jitter, idea is that instead of using the previous delay directly, we use it as a base to calculate our random boundaries, which is from 0 to 3 times the previous delay. And on average, it will grow at the same rate as an exponent with base 1.5. And with clamping, it looks like this. Okay, so let's summarize what we saw until now. Use retry to reduce impact of transient errors. Limit retrying with deadlines. Add backoff to reduce the load on the system. Use backoff strategies to balance between fast recovery and resource usage. Exponential backoff is a good default choice. In distributed systems, add jitter to avoid retry storms. And some small tips. Be careful with the last retry slip to not exceed the deadline. Consider clamping delays to reasonable minimum and maximum values. And finally, monitor and adjust your retry strategy based on real-world performance. Okay, so everything we did up until now is basically guessing. We are not sure if retrying will actually help and how long to wait until next attempt. We're just trying to do our best. But in practice, we can do better. For example, by using information provided by the server, protocol features, or API contracts. It could be information if the error is recoverable at all. What requests can be retried safely, aka idempotent? And how long should we wait until the next attempt? Let's discuss these things one by one. First of all, not all errors are recoverable. For example, in HTTP, if we get 400 bad requests, it's most likely a malformed requests and sending it again won't help us. If we get 401 unauthorized, it means we need to authenticate first, and retrying it without doing so won't help us either. Depending on the server implementation, it may also mean that authorization service was down, but if you are in control of the server, better make sure it will return different status code in that case, like 503 service unavailable, which is in most cases a recoverable error. Another example is 504 gateway timeout, which is recoverable too, but not all cases are that obvious. For example, 404 not found may mean different things. It could be because the resource was removed permanently, in this case retrying won't help, but it also can mean that the resource is not ready yet. In this case, it's a recoverable error. With other protocols, like gRPC specific status codes can be used to separate recoverable and unrecoverable errors too. In databases, there are error types. For example, log timeouts are recoverable, while syntax error or missing columns are not. Okay, so let's implement this separation in our try_fetch_sessions function. Let's first fold our backoff logic to focus on the main idea. Then let's modify our fetch_sessions function, so in case of failure, it returns an action for the color instead of just none, with an option to retry or to give up early. Then let's make our fetch_sessions function return actions accordingly. Let's retry on any network errors, but give up for any client errors with 400 like status codes, and retry in all the other cases. In practice, it could be more cautious with a specific whitelist of recoverable status codes. But anyway, let's now update our return function accordingly. First, our result is compound now, either a list of sessions or an action. Then, if it's a give up action, we just break the loop early. Otherwise, it's a retry action, so we apply the backoff and try again. Okay, so we are pretty good at retrying now, but there is one really important thing we need to consider before even trying to retry. It is idempotency. Idempotent operation is an operation which can be repeated multiple times without changing the result beyond the initial application. Because of this property, it's safe to retry such operations. For example, any immutable operations such as fetching data, select queries in databases, and get requests in HTTP, in case you don't put side effects on them which you shouldn't, they all are idempotent. But also, deleting a resource by its unique ID is also idempotent. Creating a resource, though, is not idempotent unless you provide an unique client-generated ID for it. Updates can be both, depending on the operation. If you set in a field to a specific value, it's idempotent. If you are incrementing a field by some value, it's not. For HTTP methods, it's commonly accepted that get, put, delete, and a bunch of other less known methods, such as head, options, trace, are idempotent, while post and patch are not. It is not enforced though, so be careful, but it's always a good idea to follow these conventions to make your API more predictable. Also, the good news is that we can convert any non-idempotent operation into an idempotent one by adding an idempotency token to it. For example, when user is adding a comment, we can generate a unique ID for this exact time and send it to the server along with the comment text. This way, if we try to submit this comment multiple times, either by user smashing the submit button or by our retry logic, the server can recognize we already created this comment and just ignore the duplicate requests, making this operation idempotent. In general, we can add a random unique ID, like UUID, as a so-called idempotency key. But in this specific case, client-generated comment ID will do just fine. Okay, since we are not making a generalized retry method here in this video, we just need to be sure the method our fetch sessions use is idempotent. And it is. It's a read-only GET request. So we are good here. Let's move to the next part. When to retry. With our backoff strategies, we are making guesses on how long to wait until the next attempt in hope that the server will recover by then. But instead of trying too early and failing request again, or trying too late increasing delay, what if the server could tell us when it will be ready to accept requests again? In HTTP, there is a standard header, retry after, just for that purpose. Sadly, even on the server, we cannot predict the future most of the time, but we can still use it for rate limiting. If we are throttling a client sending us too many requests, we can tell it exactly when it will be allowed to send requests again. So when we are sending 4 to 9 too many requests, it's a good idea to also send retry after header. Schedule downtime. That's not a common thing these days, but still possible, and it's a perfect use case for the retry after header. Background jobs. If server is doing some background processing, it can roughly estimate then the resource will be ready and tell the client about it. So it will retry at the right time or at least closer to it. Back pressure. Telling about estimates, when the server is under the load, we can use retry after header to apply the back pressure on clients. Idea is, the more load is, the longer retry after we send, and the clients will come down, giving the server some time to recover. So let's implement support for this header in our retry logic. Back to our code, we will need to change our file action enum to somehow store the wait time for the retry case. It is possible in some languages with algebraic data types, but enums in Python are pretty limited. So instead, we will have to move our retry case to separate data class with a field for the wait time, and do the same for the give up case. Now, fail action is not an enum anymore, but a sum type, aka union on these two data classes. It's not a perfect solution, but it's good enough. And yeah, a video about the clean code will be coming soon. So, having new type, let's update our fetch sessions function. Variant creation is almost the same, except we need to pass the delay in the branch we get the actual HTTP response. So let's get the header and parse it in a separate function. Here are 3 possible cases. The header is missing, so just return none as a delay. The header is a number of seconds to wait, so we convert it to float. And the last case is a string in HTTP date format, parsing of which is left as an exercise for the viewer. Okay, and the last step is to update our retrying function to support the new action type. And here is a perfect place to finally use some pattern matching. As before, in case our result is a list of sessions, we return it. If it's a give up action, we break the loop early. And new thing here, if it's a retry action, we get the delay from it and default it to our calculated backoff delay. So now if the server tells us how long to wait, we will respect that. We could also use the server provided delay more as a hint, for example taking the maximum of it and our calculated delay. But let's assume if the server sends it, it knows the best possible value. I want to cover many other things, but the video already took me way too long to make, so I will drop many details. The first one, and probably the most important, is the bug we have in our code with clock. We were using datetime_now Python function, which is good for checking so-called wall clock time, e.g. calendar time, but it's not good for measuring elapsed time. The reason for that is that wall clock time is not monotonic. It can go backwards, can jump forward, and in general, it's controllable by user, constantly seen by NTP, and is not reliable for measuring time intervals. That's why for timeouts and non-calendar deadlines, we need to use a monotonic clock. It's time monotonic in Python. Be careful since you cannot do many things with monotonic time, like save it to database, compare it between machines, and even between restarts. It's not suitable for calendar deadlines, like specific future dates, but it's perfect for time intervals and relative deadlines, like a point in the future 10 seconds from now. Here are a list of functions you can use to get wall clock and monotonic time in some popular languages. For timeouts and deadlines, use functions from the right column. Another little thing. In general, we use retries to hide the transient error from users, but it's a good idea to keep them visible for the developers. So, in case you do a retry, write a warning to the logs. This way you can monitor how often retries happen in your system. And in case of distributed systems, where multiple services call each other, be careful with retries. Imagine a system with 3 services, where a call to service A will require a call to service B, which in turn will call service C. If the service C becomes unavailable and all services have a retry logic in it, then it will first result in retrying from B to C, and it will happen multiple times. Then, given up with retries from B, service A will start to retry its B calls, which will again result in multiple retries from B to C. This effect is called retry amplification and can create a lot of unnecessary load and kill the system even after a minor issue, especially if the call chain is deeper and retry logic is more aggressive. To avoid problems, there are multiple strategies. Disabling retries where not needed, using shared deadline or retry budget across all services, or the final one, the circuit breaker pattern. The idea is simple, just like in your house, where if you plug too many devices into a single socket, the fuse blows and cuts the power to prevent your house from burning down. Software circuit breaker does the same. If the service is failing too often, we just stop sending requests to it for some time, giving it time to recover without any requests to it, not only retry attempts. Okay, let's do a summary for the second part. Retry smarter. Retry only recoverable errors and idempotent operations. Add idempotency key to non-idempotent operations if needed. Use protocol features, API contracts, and information from the server to optimize retries. Use monotonic clock to measure time intervals. Log your retries so you know how often they happen. Be careful with retry amplification in distributed systems. And implement circuit breakers to protect your system. Oh yeah, and before we finish, there are many libraries which implement retry logic for you, so you don't have to reinvent the wheel every time. But as always, it's good to understand how it works under the hood and why it's implemented this way. Here is a list of some popular libraries which implement generalized retry logic. Note that many HTTP client libraries have built-in retry support too, but they are not enabled by default most of the time. And now we know why. Okay, and that's all. Retry watching this video if you missed something. Like and subscribe to get more videos like this, and I will see you in the next one.